So, hi everyone. So, I want to tell you a little bit about the work that is going in my group. And essentially, we work with power electronics. Essentially, power electronics is pretty much what is responsible for making your laptop adapter or your cell phone charger too big. So, particularly the part that I'm interested in is in improving the power density of power converters. We want to make power converters smaller, cheaper, more efficient. And one of the few handles that we have as engineers in this area is switching frequency. As you can see in the power supply shown here, usually the size and volume and weight is heavily dominated by passive components. And this means inductors and capacitors. And by having switches operating on and off as fast as you can actually reduce the size of the power converters. But these techniques have their limits, particularly as in the industry in the past few decades, engineers have been increasing the switching frequency. The power density of the power converters starts increasing up to a point, and then we reach a point of diminishing returns in which further increases in switching frequency are not translating anymore into like smaller converters. You can see, for example, in the converters in the bottom of the figure, that as we increase the frequency from 250 kilohertz to 500 kilohertz, we can increase the power density from 10 to 13 kilowatts per liter. But if you double the switching frequency to 1 megahertz, the power density only increases to 14 kilowatts per liter. So it's kind of questionable whether another further increase in doubling in switching frequency would translate in something smaller. So like what my group is trying to do, which is a little bit counterintuitive, is essentially just keep increasing the frequency, but a heck of a lot more. And like the reason is, as it's fundamental that you increase the switching frequency, the size of the inductors, particularly, and transformers become smaller. And small to the point that you can actually eliminate the magnetic core that is needed to make these inductors. So essentially, you completely eliminate a source of loss, which is core losses in a transformer. And this essentially allows you to give you the opportunity to fabricate inductors by simply printing traces on a board or using just a little piece of coil around a plastic core, or just essentially print them on a printed circuit board and avoid any fabrication techniques. And we take advantage of the geometry so as to improve upon the reducing the electromagnetic fields that are accidentally emitting when we design these power supplies. And essentially, our roadmap is to make converters also cheaper to fabricate. For example, like we can go from the power converters that I built when I was in grad school to converters that essentially are just like printed with very inexpensive batch fabrication process, like the one that is shown on the right. And essentially, we want to build essential building blocks that can allow you to have very compact, very power-dense power electronic circuits. But we want to take it even further. We want to take advantage of new fabrication techniques like 3D printing, in which we can actually start fabricating components simply in the computer, and then analyze them in a FEM program and have predictions about the inductances and performance parameters that we may be interested in. And then we can just simply 3D print it in a low-cost 3D printer to fabricate a scaffold that, upon plating, it can render a component that is electrically effective and very, very, very lightweight. And essentially, later on, we want to essentially 3D print converters. So like instead of like making complicated process, you can just get your very low-cost 3D printer from the Kickstarter project that you supported, and just start making efficient power converters that are actually very lightweight. So for example, here's an example of some converters that we built that shows a 50-watt converter that uses these 3D printing fabrication techniques and only weighs 5 grams. And we're using this to essentially ignite plasmas for very interesting applications. So this is a very lightweight converter that is capable of striding a very powerful plasma. Where do we want to take this? To infinity and beyond. Essentially, we want to use this to make thrusters for satellites. If you imagine, like, there's now low-cost satellites called CubeSats that for a few tens of $1,000, you can actually start sending to space, hitchhiking a ride on a rocket, or they can be released from the space station. But unfortunately, they tend to be placed in an orbit that very rapidly decay, limiting the lifetime to between six months to 1 year. But it'll be interesting if someone can provide a solution for propulsion that can actually keep your satellite flying much longer. Essentially, we want to go from systems that has ion thrusters like the one shown here to something that is much, much smaller. So we're collaborating with the University, Australian National University, to make a CubeSat satellite propulsion thruster that we can fit in a CubeSat. And essentially, we've been, in the past few weeks, few months, fabricating this type of structures in a way that actually can have multiple functionalities. So for example, here in the middle, you can see a CubeSat, and it consists of several panels that forms a structural frame that we can replace with one of these planar converters that we're fabricating in my group. And actually, just a couple of weeks ago, we presented in the International Astronautical Congress in Australia a full implemented CubeSat 3D printer, CubeSat thruster that actually has quite a lot of room to spare. So now we can try to collaborate and find opportunities to see if we can fly one of these things. We can use them then to monitor natural resources, disaster areas, etc., at a much lower cost. And we are also trying to use these plasma generating techniques in other, for example, to implement plasma medicine applications. We want to be able to use plasma to essentially treat kill bacteria and biofilm. And also, like recently, we've been working with some high voltage power converter technologies that allow us to generate very high voltage at a very, very small volume. The reason we want to do this is we want to apply this in order to purify water, for example. It turns out that if you have a couple of electrodes and you apply a very high voltage field between 20 and 50 kV per centimeters across liquid, if you happen to have bacteria within that liquid, the bacteria kind of explode. You essentially electroporate the membranes of the bacteria. And usually this is done in a very, very large volume systems. Thanks to the technology that we're developing, we're actually able to reduce the size of this system to something that is kind of akin to the size of a Brita filter. And we've been able to test this with liquids in which we're able to demonstrate that with like a very short pulse and little energy, we can actually eliminate bacteria that is existing in the liquid. But unfortunately, water is not a very, it's not a good commercial idea. So instead, we're trying to see if we can take this to a market that is probably a little more interesting, which is milk. It turns out that about 40% of milk that is produced in rural places actually gets spoiled before it reaches a pasteurizing distribution channel. So one of the things that we want to build is it's a system, a pasteurizing system that is very, very small, that sits essentially next to the cow, that is maybe powered by solar power, that essentially that a farmer can use to treat raw milk and pasteurize it to levels that like can give them more time for its milk to reach distribution channels. And this is just a picture of one of the converters that we built. And with that, I would like to thank the Precord Institute, the Top Can Center for supporting us in part of this work, and NSF and all my students. Thank you.